From auto manufacturing plants to our homes, humanoids are gaining serious adoption. Here in the US, FigureAI bots are building the next generation of BMW cars. These are deployed in the Spartanburg auto manufacturing plant and are automating the assembly line at a galactic speed. Tesla is also joining the pack with its Optimus bot. It's being trained to automate the production line for the next generation of Tesla cars and the Cybertrucks. Germany, China, and South Korea are also leading this front with locally designed top tier humanoids. It's estimated that around 1 billion humanoids will be deployed by 2035. 50,000 are expected to ship this year alone, each engineered by robotics teams around the world. Given this scale, it's worth understanding how humanoids work. If you take a look at humanoid robots today, you will notice their design and functionality can be distilled down to 7 core systems. What are these 7 systems? Let's cover each of them one by one. Well, the first one is anthropomorphic mechanical design, or in simple words, human body inspired mechanical design. At its core, a humanoid robot is built with a body plan inspired by our own. Each of these are equipped with one head, one torso, two legs, and two arms. Each limb is made up of multiple joints. These joints are powered by actuators, or in simple terms, high power motors that allow the robot to perform a wide range of tasks. To keep it simple, this mechanical design of a humanoid can be distilled into 3 subsystems. The first one is the bipedal locomotion system, essentially a fancy way to describe the 2 legs that each of these humanoids is equipped with. The second subsystem covers the 2 spatial manipulators. These are essentially the 2 hands of the robot equipped with end effectors, or some call them grippers. A gripper is the technical term for fingers with human-like dexterity. Then, the third subsystem comprises of the torso and the neck. Each of these subsystems are powered by actuators, or in simple words, high-torque motors. They play a key role in ensuring a humanoid has a reasonable range and stability. This mechanical architecture is carefully engineered for stability, endurance, precision, and agility. Now that we understand the first core system, which is the mechanical design, we need to understand the second core system. Just because a humanoid robot is equipped with 2 mechanical legs doesn't mean it's going to be able to walk and retain its balance. It has to be trained to retain its balance. So the question is, how does it do that? How does a humanoid robot ensure that each step it takes is well calibrated so it doesn't fall? That's where the second core system comes into play. It's also known as the bipedal mobility or the bipedal locomotion system. This system ensures that a robot remains stable. It does so by helping the robot understand the terrain profile it's navigating, the slope of the surface, and the center of the gravity of the robot itself. These inputs allow the humanoid to decide what the next step should look like. We call this gate planning in the world of robotics. Basically, it means determining what kind of footstep pattern the robot will choose for the next step based on the current parameters for the current step. How does it do that? Well, there are 2 ways to approach this challenge. One is to simply take the real-time data from sensors such as the force measurement sensors located on the feet, the cameras, and the IMU sensors. Then use this data to understand how the ground profile is changing. Based on these changes, a humanoid can respond by activating corresponding actuators or motors located around the legs. These actuators apply appropriate torque to ensure the robot has a firm grip on the ground. Some refer to this approach as a reactive approach. An approach that is more proactive, on the other hand, relies on the principle of prediction, or in mathematical terms, computing probabilities for terrain profile based on historical data. So instead of just relying on the real-time data received from sensors for the current step, a humanoid scans the terrain, takes the current and the historical data from the past few steps, and then it predicts how the terrain profile is about to change. It then adjusts its next step or selects an appropriate gate. We call this gate planning in the world of robotics. This ensures our locomotion system is aware of the current and the historic patterns the robot has encountered in the given environment. In simple words, it's a self-aware locomotion system. This core system too is fully responsible for retaining balance and ensuring the humanoid is able to move around in factories, warehouses, and homes with the highest levels of ground grip, precision, strength, and stability. Now you might ask, well, that's for mobile navigation. What about if our humanoid has to lift an object or pick an egg from a packet? How does it do that? This is where the spatial manipulators come in handy. A spatial manipulator is a technical term used to describe arm with human-like dexterity, and an end effector is a technical term used to describe fingers or grippers that can be controlled electronically to grasp an object. Most humanoids today are equipped with two spatial manipulators, each equipped with strong end effector. From a mechanical perspective, these are essentially metal parts or limbs powered by high-torque motors that provide a range of motion. We refer to this as degrees of freedom in robotics or DOF. So if you hear folks say 3DOF or 4DOF, just know that that means those are the number of motor control joints present in each spatial manipulator. Why does that number matter? Well, if a humanoid arm has more joints, that means each of these joints can be moved in different directions and at different speed. Hence, a humanoid can potentially perform thousands of types of movements. In simple terms, more UFs means more range of motion, and that means ultra high capabilities for our robot. We humans have 7 degrees of freedom in each arm. That means we have 7 core joints. 3 of them are located in the shoulder, 1 in the elbow, and 3 in the wrist. DOF choice for humanoids is inspired by us humans. Now that we have covered the first 3 core systems, the question is, how does our robot make decisions? How does our humanoid know how to move these spatial manipulators to pick an object? Objects come in different shapes and sizes. An apple is different from a car part that a humanoid may have to move on an assembly line. So, how does it make a sense of these objects in the real world? That's why we need sensors and the perception system. It's the fourth core system of our humanoid stack, and essentially the robot's way of understanding its surrounding and making well-calibrated decisions. Question is, how does it work? We cover the full system architecture of humanoids in our course on applied robotics. We teach robotics with core principles and real-world case studies, from space rovers and legged robots to humanoids deployed in factories all around the world. You will learn the exact approaches adopted by each of these teams to bring these robots to life. Most importantly, you will gain deeper professional expertise. Expertise that companies demand and the ones that will set you apart in the interviews and at your job. You will find the link to the course in the comments. Now that we have seen some of the core components of humanoids, you might be wondering, where are these deployed? From the auto manufacturing plants here in the US to homes around the world, humanoids are experiencing galactic adoption. This adoption trend started in early 2024 when FigureAI bot, a humanoid developed here in the US, got deployed in a real-world production facility, that is at BMW Group's Spartanburg plant in South Carolina. This marked a milestone for both companies, the first humanoid robot tested in a live automotive manufacturing plant. Over the next few months, the FigureAI team analyzed the performance data from this trial and optimized the underlying AI model used to train this bot. This led to the launch of FigureAI bot at the same plant. Some of you might be wondering, what exactly did FigureAI bot accomplish during this trial? During this trial, FigureAI was primarily responsible for automating the chassis assembly process. It was tasked with placing metal parts into specialized fixtures which would then be assembled as a part of the chassis for the next generation of BMW cars. So, did it pass the test? Yes, it did. During this trial, it demonstrated not just spatial precision down to the millimeter level, but also extremely high dexterity using its 16 degrees of freedom human-scale robotic hand. For BMW, this trial is a part of its broader iFactory initiative, a forward-looking program focused on building smarter, agile, and more sustainable auto manufacturing plants. In this context, humanoids are being evaluated to handle tasks that are awkward, tiring, or ergonomically risky for human workers. Beyond auto plants, humanoids like Neo are also getting trained to serve as home assistant. Developed by the 1X team, Neo is designed to assist us humans with our daily chores and make us more productive. Neo is not the only one leading this front. If you look around the world, Optimus in the US, R1 in China, and R1 Cube 3 in Italy are just a few examples of humanoids that are being trained to help us both in our factories and at our homes. Over 50,000 will ship this year alone, and about 1 billion are expected to inhabit Earth by 2035. There are thousands of jobs originating in this domain, jobs that demand professional expertise beyond theory and projects. Hence, we have launched our course on applied robotics. This course is designed to help you build deep professional expertise that companies demand and the ones that will set you apart in your interviews and at your job. From Mars rover and mobile-legged robots like Spot to humanoids like Optimus, Neo, and FigureAI, you will see how these robots are built and deployed from scratch in the real world. You'll find the link to the course in the comments section. Join 80,000 students from 150 countries, kickstart your career with Coding Sage.